Welcome to Complex Analysis. Today we are diving into the fascinating world of complex mappings. If you have ever wondered how we can visualize mathematical functions when both the input and the output are inherently two-dimensional, you are in exactly the right place. We will build this intuition from the ground up. Let us begin our journey. To understand why complex mappings matter, we first have to look at how we visualize math. In standard calculus, you graph a function on a single flat page because the input is a one-dimensional line and the output is a one-dimensional line. But in complex analysis, our input is already a two-dimensional plane and our output is another two-dimensional plane. To graph this normally, we would need four dimensions, which our human brains simply cannot visualize. Therefore, instead of one single graph, we use two separate flat planes side by side. The mapping acts as a bridge between them. Now that we know we need two planes, let us define our starting point. This formula represents our input plane. Conceptually, it gives us the exact horizontal and vertical address of a dot on our starting map. The symbol Z represents our input complex number. The variable X stands for the real part, which tells us the horizontal position on our input map. The variable Y stands for the imaginary part, which dictates the vertical position. If you increase X, the point moves to the right. If you increase Y, it moves up. Together, they pinpoint our exact starting location. Moving from our starting map, we arrive at our destination. This formula defines the output plane, where our transformed points finally land. The symbol W represents our final output complex number. The variable U is the new real part, giving us the horizontal coordinate on the destination map. The variable V is the new imaginary part, providing the vertical coordinate. Just like before, changing U shifts the point horizontally and changing V shifts it vertically. This entirely separate map is where we see the final result of our mathematical teleportation. With our input and output planes defined, we need a rule to connect them. This is the master equation for complex mappings. The function f of z is the mathematical bridge between the two worlds. Notice carefully how both the new horizontal position u and the new vertical position v depend on both original coordinates x and y. This is a crucial concept. A simple change in just the horizontal input can drastically alter both the horizontal and vertical outputs. This interconnectedness is exactly what causes the stretching and twisting we see in these transformations. Before we calculate anything, let us see this visually. On the left, you're looking at the z-plane, our input world. Notice the horizontal x-axis and vertical y-axis, and the simple blue square resting there. On the right is the W-plane, our output world, with its own U and V axes. The curved arrow in the middle represents our function, f of z. It takes every single point of that blue square, processes it, and maps it to the right side. The result is the red shape, which has been stretched and rotated into a rectangle. Now that we have a visual understanding, let us look at a basic numerical example to see how a single point moves. We are given a specific starting point, z equals 2 plus I, and our mapping rule is w equals 3 times I times z plus 1. We need to find exactly where this point lands. Our first step is to substitute our given input directly into the mapping function. Next, we distribute the multiplication across the terms inside the parentheses, carrying the imaginary unit along just like standard algebra. Continuing with our calculation, we must deal with the squared imaginary unit. We apply the core rule of complex numbers, replacing I squared with -1. This is a crucial step because it converts an imaginary-looking term back into a pure real number. Now, we simply combine our real numbers, adding -3 and +1 to get -2. The imaginary part remains +6. Physically, this means our original point at coordinates 2, 1 has been moved and rotated to land at -2, 6 in the output world. Having mapped a single point, let us tackle a slightly harder example, where we map an entire infinite shape. We want to find the image of the vertical line defined by x equals 1, using the squaring function, w equals z squared. A vertical line means the real part is permanently fixed at 1, but the imaginary part y can be any real number. We substitute this generic line equation into our squaring function. Then, we expand the squared term using standard algebraic rules for binomials, representing every point on that line being processed. Moving forward with our expansion, we must carefully simplify the expression. Since the imaginary unit squared is -1, the final term changes into a negative real term. The middle term remains imaginary. Next, we group the real parts together and the imaginary parts together. This successfully separates our output into its fundamental components. The portion without the imaginary unit is our new horizontal coordinate, u. The portion attached to the imaginary unit is our new vertical coordinate, v. We now have two separate equations defining our new shape. To understand the final geometric shape, we need a single equation connecting u and v, eliminating the original vertical variable y entirely. We start with the equation for our new imaginary part, v equals 2y. By dividing both sides by 2, we isolate y. This gives us a direct way to substitute it out of our system. We take this fraction and plug it directly into the equation for our new real part. This is a crucial moment, as the original input variable is now completely erased from our system. For our final step, we simply square the fraction by squaring both the numerator and the denominator. This leaves us with our final simplified equation relating the horizontal and vertical coordinates of the output plane. In coordinate geometry, an equation where one variable is linear and the other is squared represents a parabola. Specifically, because of the negative sign, this equation describes a parabola that opens to the left along the horizontal axis. Physically, this proves that our mapping took a perfectly straight vertical line and bent it into a curved parabola. You might be wondering why bending lines into parabolas matters in the real world. In engineering and physics, professionals constantly face boundary value problems, describing how heat or fluid behaves around complex physical edges, like a curved airplane wing. Complex mappings allow engineers to take a complicated, ugly shape and mathematically map it into a simple, clean shape, like a straight line. They solve the easy problem there and map the solution back. This technique, especially conformal mapping, which preserves angles, is a foundational tool in designing aerodynamic vehicles. Let us summarize the key takeaways from our journey today. First, remember that complex mappings are mathematical translation tools that convert points from an input grid to an entirely separate output grid, because we cannot visualize 4 dimensions at once. Second, the mapping function dictates exactly how shapes warp, stretch, and move. Third, by separating the output into real and imaginary parts, we can track exactly what happens to any geometric shape. Finally, this is not just an abstract trick. It is a powerful lens that simplifies impossible physics problems. Great job following along.